Welcome back to the Lowdown on Physics. This is Screencast number 1 for the series Radioactivity for Unit 1 Physics. Today we'll be looking at atoms, isotopes and radioisotopes. Often the best way to understand what's going on with a new concept is to go back and actually have a look at how that idea has developed. So we're going to do a quick review of the development of the model of the atom. So the ancient Greeks, by the 5th century BC, so we're talking good 2,500 years ago, understood that each atom was individual, that each element had its own atom. But the question was, what did it look like on the inside? Now, it's only really the last 100 years that has given us a massive amount of understanding into what's actually the makeup of the atom on the inside. So 1896, so 120 odd years ago, was the dawn of the nuclear age, and that's what's given us so much insight into the construction of the atom. So Henri Becquerel, he discovered radioactivity in uranium salts. That led to Marie Curie's discovery that it's not actually a chemical effect, but it's a particular phenomenon. It's something that's only associated with a few elements. This led to J.J. Thomson discovering that all elements contained identical negatively charged particles inside, and he put forward this idea of this plum pudding model where there was just like bits of plum in a pudding. These electrons were just scattered all throughout the this positively charged dense atom. From there, the next major discovery was by Millikan, and basically what happened was oil was sprayed through this. It went through these charged plates, and it was ionized by radiation here, which would basically cause the oil particles to have a charge, and they would then, using the two charged plates, fight against gravity and keep it balanced in midair. What this showed was that yes, there was in fact a charge associated with these atoms. From there, Rutherford went on to find 3 types of radioactivity: alpha rays, beta rays and gamma rays, which make hulks. And from there, our atomic research basically continues on. So using sort of those discoveries, that will give us the foundation to investigate the nature or the design of the atom, and then use that to explain what we observe in terms of radioactivity. We've been told since we started science in Year 7 that atoms are made up of 3 things. We've got the protons, the neutrons in the nucleus at the center. It's a dense center, and the electrons are orbiting. Most of the actual atom is empty space. To put that into a bit of context, let's say that the nucleus was the size of a pea, a single pea. Now, if we were to take that pea and put that inside the MCG, then the electrons would be orbiting all the way around here. So it just gives you a bit of an idea of, once we put relative size to it, how much space there is inside the atom. Okay, we should also be familiar with the charge on each of the atoms. Proton positive, neutron has no charge, neutron neutral, electron is negative. But interestingly, look at the mass. The majority of the mass comes from the nucleus. Okay, the electron is a smidgen of the mass of the components that make up the nucleus. So if we look at these two, they're identical in size, they're identical in mass. The only variation, though, will be that one is charged, one is not. Now, to produce a stable atom, there's going to be some forces that are going to hold it together. Now, if we think about the electrons and the protons. There's electrostatic forces. These are the attraction between the positive and the negative, or the opposite charges. And this is quite a strong force. But yeah, it's that attraction between the protons and the electrons that will keep them in orbit. Now, the other thing that's going on is, other than hydrogen, atoms have more than one proton. Now, since it is a strong force, the repulsive forces would in fact blow the atom apart if there wasn't something else there to prevent that from occurring. That other force is called a nuclear force. Now, this is a pretty intense but short range force, and it's between the protons themselves, protons and neutrons, and between neutrons themselves. Now, it's basically it's a really vital force, and we need neutrons there because it's going to resist that repulsive force of the protons and stop it from blowing itself apart. So the neutrons are effectively becoming an insulation between the protons. Now, when we're describing an atom, there are two really important terms that we need to be familiar with. First is the atomic mass, and both of these terms will come from your periodic table, and it's the total number of protons in the nucleus. The second is the mass number, and it's the total number of protons and neutrons in an atom. Now, when we're doing nuclear decay series later in the topic, we will represent it like this. So X will be the symbol for the element, A is the mass number, the larger of the two, Z is the atomic number, the smaller of the two numbers. So it's important to recognize that the atomic number is what defines the element. So all elements with the same Z are the same element. So if the atomic number is the same, then they are the same element, even if A is different. Okay, so all A does is tells us that it has a different number of neutrons. So when we're referring to a particular nucleus, we often refer to the nuclide, and that's really talking about what's happening in the nucleus, ignoring the electrons and what's happening there, particularly in these radioactive decays, because yeah. So just going to have a quick look at an example where we're given some element. Now we've got two numbers there, 53 and 127. 53, the smaller number, that's the atomic number. That's the one that defines the element. We use that on the periodic table to help locate the atom. So we look for number 53 in the atomic number, and what that does is that identifies that the element must therefore be iodine. Looking at that, we could take it a step further and say, well, with that information, there's 53 protons, must be the same as the number of electrons, and the difference between those numbers is 74, and that is the number of neutrons. Now, all atoms are the same element. I mentioned this a moment ago about the difference with neutrons. All atoms of the same element will have the same number of protons in the nucleus, but there may be a different number of neutrons, and this is what we call an isotope. For example, lithium has two isotopes. We've got lithium-6 and lithium-7. So the first one has three protons, 3 neutrons. The second one has 3 protons and 4 neutrons. Generally, the one that's listed on the periodic table will be the most common of the two isotopes. Now, isotopes still react the same way chemically. The neutrons play no part in the actual reactions. The difference, or how reactive it is, the differences lie in its physical properties. Now, basically what it means is more neutrons gives us a denser atom. Now, radioisotopes. The name would probably suggest what's happening here, but most atoms are stable. Some isotopes are unstable, and we call them radioisotopes, because they are radioactive isotopes. So for example, we've got carbon-12, carbon-13. They're both stable isotopes. Carbon-14, however, is not. And in general, when we look at the periodic table, everything that's above bismuth is radioactive, as well as two others. We've got technetium and promethium. Now, an unstable nucleus may spontaneously lose energy. Basically, what that's saying is that they may just spontaneously, you can't predict exactly when, it will just decay. It will basically throw something out and become a different element. Now, often this may be quite dangerous, the particles that are emitted. Now, there are a few natural radioisotopes, but many of them are in fact produced artificially, and mostly for medical or industrial uses. But we'll talk a little bit more about that later. That just gives us a little bit of grounding in terminology and stuff. So that's it for now, and I'll see you in class